Right.
Or stay half an inch.
That's okay. Right. Now, okay, we're starting off with Big Bang Theory. We had a look at this the other day. We just introduced it as an idea. I had a look at the key learning intentions that are covered on this particular slideshow. You know, what is the Big Bang? We'll watch a video today as well to help us out. So we'll take a few notes. This I mentioned the other day was prior knowledge. Hopefully everyone knows that a moon orbits a planet orbits a star, and then it goes from there. Stars orbit galactic centre, if you want to get picky. Does anyone know what's at the centre of galaxies?
Black holes.
Black holes. You need something of incredible gravitational attraction to keep in order 400 billion stars, and black holes will do the job. Okay, supermassive black holes. And then we've got galaxy universe. Okay. We had a look at this the other day. You took some notes. I want to just emphasise again these key points. Just quickly, did I ask you the other day, what does it mean by 8 minutes 19 light seconds away? When we say the sun is 8 minutes and 19 light seconds away. Yes?
Is that how far away it is? With light speed?
Yeah, relative to light speed. So that's something that students struggle with. There's always a 1 mark question. This star is 4.1 light years away. How long would it take light to get from that star? And students, it's really that simple. 4.1 light years. 4.1 years. What is the speed of light? 300 million meters per second. It's actually in there, probably on the next page. 300 million meters per second. Can you go faster than light speed in this universe? No. That's a hard and fast rule. As you go faster, time goes slower, awesome, but you gain mass. And so you can't go beyond light speed. And what's really weird is if I shine a torch at you, the light beam reaches you at light speed. If I'm riding on top of a speeding train on a motorcycle that's also speeding and shine a torch at you, so I'm coming towards you, speed of the train compounded by the speed of the motorcycle, the light beam still approaches you at light speed. It doesn't go faster than that. Okay. And of course time does dilate. So as you go faster, you go slower. And that's not theoretical, that is literal, because they've done that with satellites. So you have two very, very finely calibrated, effectively stopwatches. Leave one on Earth, you put one in space on a satellite doing maybe 30,000 kilometres an hour. You come back and they're out of sync. The one on the satellite, time ran slower. Okay, so if you were on a spaceship moving close to light speed, you'd be eating 3 meals a day. Every few hours you go, I'm a bit hungry. All your biological processes are functioning normally. The watch on your hand is running, etc., etc. And you travel like that for a year and you come back to Earth and everyone you know has died of old age, as have your children probably at that stage. And maybe even your grandchildren are struggling. Okay. So, yeah, it's one of the neater aspects of the universe. The sun has a core temperature of 15 million degrees. That's the core temperature. That's for fusion to occur. But the surface temperature is 5,500, which classes it as a yellow star. Note the difference. The surface is almost cool in comparison. Okay, so all stars are fusing hydrogen into helium. That's true of all of them. Okay, but in this case, because it's quite a small star, it's got a lower surface temperature, maybe 5,500 degrees. Star surface temperatures can go up to 40,000 degrees, and so you get different colours. Okay, lifespan, about 10 billion years, 98% of the solar system. We talked about hydrogen being converted into helium. We did the math on how many Mount Everest of TNT that would be. But it is a tremendous amount, 600 million tonnes of hydrogen per second by 10 billion years. Okay. Now, let's see. Any questions about that? So, emphasise those key points. Okay. Next. I think we talked a little bit about this. I didn't, and I haven't brought a pen with me, which is a bit silly, but did I emphasise over at this end that this is high frequency, high energy, and you need to write that down? So make a note, high frequency electromagnetic waves, and high energy, okay? And these ones down here are low frequency and low energy. And you need to write that down. Now, these three here are special. Did I mention why they're special? The ionising radiation. Well, okay, from year 9, chemistry, nuclear, gamma radiation. How readily does that penetrate materials? Anything but lead. It'll do lead too, just you need thick enough, yeah? About 1 metre of concrete it's good for. Okay, so if you were hiding behind, that wall as a gamma burst went off, it's not going to preserve you, and you're not going to become a superhero. You're going to become soup. All of the DNA in your body is going to fragment rapidly, and if it was a significant enough burst, you'd actually just stop. As from our perspective, you just go slump, and you've died. There'd be no physical. We'd be just looking at you, going, well, that's a dead person. That's going to be a lot of paperwork. But physically, you look okay, but at the level of your DNA, you would have been fragmented. Okay. So, you guys didn't see the elephant's foot in year 9 chemistry for Chernobyl? The elephant's foot is the melted core of the Chernobyl nuclear reactor, because it looks like a big elephant's foot. And it's sitting in the basement of one of the buildings because it melted out of its containment chamber and went 1 story down, okay? And they were desperately trying to stop it from hitting groundwater, because if it did, it would have gone off like a bomb and killed Europe. So, but it was so radioactive that they sent a robot to try and get a picture of it, and the robot failed. So how do you get a picture of something that is pumping out everything, including X-rays, gamma rays, ultraviolet? Well, you stand around the corner and you use a mirror, and that's what they did. Mirror on a stick. So, and they're able to get a photo of it. One of the people at Chernobyl who, when this thing went bad, he ran onto the top of an adjoining building and he glanced over to see, get an idea of what was going on, and he died. Not immediately, but pretty rapidly. That glance over the top of the parapet was enough to pick up a lethal dose of gamma. These are all, so for these ones here, put a bracket and put DNA damaging. That will work. DNA damaging. Ultraviolet will get through a layer or 2 of your skin cells and can damage DNA. It's got enough energy to do that. X-rays, you already know. If you have an X-ray, it goes through all soft tissue but not bone. So you get a silhouette of the bones, and you can see there's a break, which is very handy. But gamma rays just go right through you. Okay, bone, everything, because they're so high energy. Now here's here's a key point. All electromagnetic radiation consists of photons, and a photon is effectively a massless particle. It acts like a particle and it acts like a wave, depending on what you're doing with it. And they move at light speed, which is 300 million metres per second. And if it's red, it's important. Did I emphasise that point?
Yeah.
On the slide shows, if it's red, it's important. It's going to be insane. And they're moving at 300 million metres per second. So, how quickly are radio waves moving? 300, this is not a trick question, 300 million metres per second. How fast are the super energetic gamma rays moving?
Light speed.
300 million metres per second. Light speed, light speed, light speed, light speed. They're all forms of light. You, in your everyday language, think of Roy-G-Biv down here, and you can put Roy-G-Biv. Everyone put Roy-G-Biv. Red, orange, yellow, green, blue, indigo, violet. Put that down. That's really valuable. Okay? It'll help you, because at the red end of the Roy-G-Biv, what's beside red? The red end of Roy-G-Biv, invisible light, infrared. And what's beside the violet end of Roy-G-Biv? Ultraviolet. You know Roy-G-Biv?
How do you spell it?
Roy-G-B-I-V. Red, orange, yellow, blue. Red, orange, yellow, green, blue, indigo, violet. Okay? So when we say light in everyday language, we think in terms of visible light. These are all forms of light. They all propagate by photons. They all move through space. They don't need atoms like sound does. I'm talking to you. I'm vibrating the atoms in the room, in the air. You're hearing them. Okay? And so they don't require that. Now, so literally, the sun produces radio signals. Okay? It produces everything in that spectrum. So later on we'll have a listen to the radio signals from the sun. And it's not very interesting, it's just a hum. But it's going, it's detectable. Okay, so now this we didn't get to the other day. Good old Earth's atmosphere, fine. The sun emits energy as photons, and some of them you can see, some you can feel as warmth, some you can hear. The Earth's atmosphere is only transparent to some of them, thankfully. We're close enough to the sun for, if there was no atmosphere, the gamma radiation would just, this would be a lifeless ball. Okay, the sun is incredibly titanically violent. Okay, ultraviolet radiation, most of it gets blocked. What is the blocking layer in the atmosphere for UV?
Ozone layer.
The ozone layer. So put in ozone. You're going to need that in ecology in 10 months' time. X-rays, blocked. Yay, X-rays. Gamma rays, blocked. Fantastic. And of course, if you're an astronaut and you're above the atmosphere, this is a real concern. If you wanted to travel to Mars, and potentially, you're young enough, some of you might, they're going to try and establish a colony on Mars in the reasonable future. One of the key considerations, no atmosphere on Mars, so you dig, or you get into a lava tube cave and live there, okay, to protect you from that radiation, bathing the planet at all times. Radio waves we can detect at the surface. Infrared, of course we can detect that at the surface. Mind you, not all of it gets through, but you go outside, it's pleasantly warm. If I put you above the atmosphere, so really the same distance from the sun, you're going to be roasted. Okay, it's going to be incredibly unpleasant, close to 200 degrees, but quite pleasant at this level. And visible light, of course, gets through, otherwise we'd be having this class in the dark, and it would be not as effective. And then I have a cool video of someone standing in unfiltered sunlight as well. That's stylised, it's from a movie. Not all the sun's energy reaches the surface, thankfully. Any questions about that there? No? Crystal clear, hopefully. Now, the Doppler effect. Okay, who's ever heard a car beep their, or a train? Who's ever been standing on a train platform and the train goes past blowing its horn and it goes meow, meow as it goes past, yes? Does it make the same sound if you're the driver of the train listening as you pull the horn? No, for him it just goes meow, it's the same tone. Okay, so what is happening? Here is a little person standing on the street as a rude driver approaches blowing their horn. Now, as the car moves away, you see the wavelengths from the horn are quite long. As the car approaches, the wavelengths from the horn are quite short. Okay, so as the car's moving, it's pressing the waves together, if you like. They're being compacted as you approach the observer. And as it goes away, the wavelengths are stretched. This is also true for the electromagnetic spectrum. Okay? See, the Doppler effect is an increase or decrease in the frequency of sound or light or other waves as the source and the observer move towards or away from each other. We say redshift when objects are moving apart. So if you were running away from me at close to light speed, you would appear red, literally, because the white light bouncing off you would be stretched out by your incredible velocity. If you were running towards me at the same velocity, you would literally have a blue shift to you. Okay? This is what the rocket ship is for. Remember the rocket ship, circle it, put a big arrow, I don't care. If the rocket ship is moving away from you, what colour do you see?
Red.
Red, from the engine. If the rocket ship is moving towards you, what colour do you see?
Blue.
Blue. If a galaxy is moving away from you, what colour do you see?
Red.
Red. It red shifts. Okay? And if you went out and had the appropriate equipment and you looked out into the universe, what colour would the galaxies be shifted to? Would they be stationary relative to us, so no shift? Would they be red shift, blue shift, or a combination of all three? What do you think? All three? It's red, 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 red. So what does that tell you about the universe?
It's red.
No, it's moving apart. So what does that tell you about us? Are we the centre of the universe and everything's moving away from us? No, we're also moving. Okay, and that is a key observation for Big Bang Theory. The fact that when you do those measurements, you see that galaxies are moving apart from each other in all directions. So the first thing that tells you is the universe isn't static, whereas everything just sitting there. And the second thing it tells you is if everything is moving apart, then at some stage you would expect everything at one point was together. Okay, and that's what we're going to get to next. You'll need to be aware of redshift and blue shift, because the whole redshift thing is a key piece of evidence for Big Bang, that the universe is expanding. There's no doubt about that, and that's considered the key point of evidence for Big Bang. Okay. Now, there is quite a big diagram about the Big Bang. We're not going to don't worry about even reading or trying to memorise that. I've got a summary of what you need to do. That's on the last slide. But what is the Big Bang? In a nutshell, without reading. You can cheat.
When the universe started?
When the universe started. So what was there?
Nothing.
Nothing. Okay. What they say is a singularity. So the entirety of the universe was packed into a point of space-time. Okay, and then it started to expand rapidly. We'll watch a little video about that. And so yes, you have this incredibly dense point, almost infinitesimally dense point that then rapidly expanded. At that point, temperatures were incredibly high. Energy and matter were interchangeable. There are four key forces, if you like. There's gravity, the weak one. Then there's the strong nuclear force, the weak nuclear force, which are responsible for keeping atoms together. And then you have electromagnetism as the fourth force. But at the early stage, there was only one force, and that split into those four forces. So everything in terms of physics and things that you intuitively understand, none of that would help you at that point in the universe. It's not comprehensible and a real thing. The universe, one of the key attributes of this universe is space-time. You may have heard that term, space-time. The students sometimes ask, what was before the Big Bang? Well, time is an aspect of this universe. It's a property of this universe. So there was no before the Big Bang because there was no time until the universe came into existence, which is weird. Okay, so there's a few other weird things. The other weird thing about the universe, the model that we use to describe the universe is an inflating balloon. So remember, the universe is effectively four-dimensional, but we use something simple like a balloon expanding. If you were an ant on a balloon running around on its surface, could you ever step off the edge? No, that you're just running around the surface like we do on the Earth. Yeah. So there's no edge to the universe. You can't get there and go, ho, ho, ho. You know, there's no getting past it. Yes, if you had a really powerful, magical telescope, it would have to be, and you stared out into the universe and broke a few laws of physics, you would be able to see the back of your own head because you'd be capturing the light. The universe is curved. Yes, it's an expanding curved surface. So think of it like, you know, if you go in one direction on the Earth, flying on an airplane, you ultimately do a lap and come back to where you started from. And the universe is working the same way. There's no getting to an edge. There is no edge. It works like that inflating balloon. So you'll see here some numbers. Very short period of time, 10 to the minus 43 seconds. So 0.0000 for about 42. 1 seconds. This was happening, and then this was happening. So quite a bit was happening before you get to this point of 3 minutes. There's the 1 second mark, there's 3 minutes, there's 300,000 years, and that's when we start to see electrons forming and things like that. So this is the kind of things that you're familiar with, whereas everything that was happening here was quite unfamiliar. And it's a little bit intimidating, so let's go there. I'll go to the last slide. It's the last one you have. You'll notice the red on this section. That is the key thing that you need to understand. And let's have a look at this idea of the Big Bang. Okay? So, all time, space, energy concentrated into a single point singularity. Okay? And then when it goes off, time and space begin. Both time and space begin. Space expands quickly. The temperature is ludicrous. You don't need to remember this so much, but let's just look at 10 to the 32 degrees. So incredibly hot. Okay? Now, 10 to the minus 34 seconds. You don't need to remember the time so much, though I did see a question once about this time period. 10 to the minus 34, the universe is the size of a pea. Electrons and positrons are starting to form at this point. Electrons and positrons. What's a positron? It's like an electron, but it has a positive charge. But we don't test for positrons. If down here, I want you to draw an arrow pointing down, put the word small, put the word large. It's that simple. The smallest thing that you're familiar with from chemistry, electrons. Yeah? And then if you go down, electrons, then we get protons and neutrons, then we get atoms, or nuclei, then we get atoms, then we get planets and stars, then we get galaxies. It goes in that order from smallest to largest as time passes. Okay. After a little bit more time, so it still hasn't not even 1 second has passed at this stage, protons and neutrons are formed between the smaller particles. I won't get into that, but yes, this is the formation of protons and neutrons at this stage. Then the universe is the size of a solar system, and not even a second has gone at this stage, 100th of a second. No true atoms have been formed yet. It's just too hot. Okay? Atoms, what is temperature when we talk about temperature? What are we talking about? Yep.
The movement of atoms.
Yeah, the movement of atoms, the vibration of atoms. Okay? What's absolute zero? No movement. So what's the temperature that no movement occurs in this universe? Does anyone know? It's actually written in there, but it's just not on that. Negative 273.15. At minus 273.15, all atomic motion stops. That's absolute zero. So that means that the atoms are no longer moving at all. So you can't get less than no movement. So these upper temperatures in the universe, you can get to ridiculous temperatures in terms of high temperatures, but low temperatures, minus 273, you think is almost survivable. Like if you had a really good set of thermal underwear and a really good woolly jacket. That's my challenge for the boys in the back row. If I had a room that was 10 metres across and I just gave you really thick clothes, could you cross that room? It's normal, for normally, to run that distance, we'll say 3 seconds. Okay? So it's not even very far. It's about the width of this room. 3 seconds. You're going to go through a force field on one end, so you don't have to open a door, run across, go through a force field on the other. And you've got thick clothes on. Could you do it?
No.
No? Why?
Stop moving completely.
Would you?
As soon as you get.
It's pretty cold in space and they're trucking around for hours up there. They do spacewalks for hours.
Well, if you're like a world record long jumper, and you
long
just jump
jump
the
and
whole
gravity.
thing.
Oh, I see. Interesting. Yeah, that might... Oh, no, I don't think you can't jump that far.
What if you just stay home in bed? instead?
No. What would happen to the atmosphere in the room at minus 273.15?
No idea.
Think about it.
It would just stop.
Yeah, the atoms aren't moving. So what happens? What happens when I cool things down?
It would be like hitting a wall.
What would a 6-year-old tell me if I said, what happens if I cool things down in the freezer?
It gets cold.
They freeze! Okay, which means they become a solid, which means that room has no atmosphere, it's a vacuum. So you've cleverly avoided my trap, because you would have died a horrible, horrible death. It's a deep vacuum at that stage, and you're not used to that. You know, your lungs would expand. Holding your breath was exactly the wrong thing to do. They'd pop before you even got halfway. And then, of course, all your other blood vessels and everything else would be going wild as well.
We should test that.
I don't need to. Haven't you ever seen the video where they take a balloon? They take a balloon and they put it in dry ice, and the balloon just whoosh, goes down, and then you open it up and crystals come out, and that's the air crystallised. Okay, it's the same thing. So we'll have a look at absolute zero in a bit. But here we go. At the 1 second mark, we're still at 10 million degrees, which is really, really hot. And then it's still cooling down, cooling down. At 5 minutes, we start to get nuclei forming. So we've got the nucleus of an atom forming. And then at this point here, after 300,000 years, the very first atoms form. Please highlight hydrogen, helium, lithium. That was our early universe. If I had to give you a chemistry exam at that stage, you would ace it. Because I had 3 elements to work with. No molecules, just hydrogen, helium, lithium. Okay? And then where did the other elements come from? Stop, magic. Where did the other elements come from? Oh, hang on. Yes. Just joining together, hanging out. Isn't that a molecule? What we talked about this before. What are elements? Like when I say, how is the periodic table organised? In order of protons. Okay, so you can't just they can't just hang out and form a bond. You have to jam them together hard. What's a machine that can jam things together really hard at high temperature? Sun, star, anything like that. Until you get the first stars and planets, and you know the sun converts hydrogen to helium. The sun will actually take hydrogen all the way up to carbon. Okay? And then the next generation of stars will take everything all the way up to iron. And then if you get a supernova, you can get everything up to uranium. And that's how you build elements. You jam them through stars. So all of the carbon in your body and the gold in the Central Deborah gold mine and everything you know and love has come through a star first. So theoretically a star poop. Okay, there we go, first star. Look, I even said it there. Fusion of new elements. Swirling clouds of matter around some stars cool and clump, leading to the first planets. That's just embarrassing. The answer is on the next line. And the universe becomes lumpy, gravity starts to pull matter, first galaxies form, boom, off we go. Okay? And so that is the history of the universe in a nutshell. Now, we'll go up there. That's Big Bang. Let's look at some evidence for Big Bang. Okay? Steady state theory, version 1, was that the universe is unchanging, no beginning and no end. And certainly, sure, people aren't silly. They knew that the stars, there was variation. They thought that the big disk was moving across the sky, but of course, the planet itself is both turning and orbiting the sun. Okay? But the stuff does change up in the sky. But the general theory of this is the universe is unchanging. There was no beginning, there'll be no end, and off you'll go from there. A few hiccups along the way. Every so often a supernova would go off, and it's very detectable. There was one, I think it was in the 16 or 1700s, where for about 3 months in the sky, this second sun was in the night sky, and you could read a book at night. Okay, when a supernova goes off, when a star explodes, that one star, for a brief period, is putting out more energy than all the other stars in the galaxy combined. And that's 400 billion stars, and it's pumping out more. So they're energetic.
And it dies.
Okay, and then it dies. In an exotic way.
Wait,
1929, Edward Hubble did what you did. He observed that in every direction you look, galaxies are redshifted. What does redshifting indicate?
moving away from the
Moving away. Remember the rocket. Remember the blue rocket. You see the red motor? It's moving away. They're moving away from the observer. Now let's do a little bit of graph analysis. Students really struggle with graph analysis. So I always say, look, there's a line. Oh, that seems to be a trend because all the data points are on the line. So what's the general trend? Don't ever get into the habit of trying to talk about each point individually. Point A is this distance and it is this speed. Point B is this distance and this speed. We know all that. What is the trend? How do you establish a trend? Look at something simple. What about this first point down here? What have we got on our axes? Our independent variable is distance. Our dependent variable is velocity. Okay, so how far away is that point there from us, the observer? Close or far? It's pretty close. We don't know what this unit is. We don't know what this... Oh, we do actually. It's distance in megaparsecs, I think it is. But it's pretty close. How fast is it going? Fast or slow relative to this axis?
slow.
Pretty slow. You know, I mean, these are significant velocities relative to a car. It's fast, but compared to this axis, it's pretty slow. It's got a low value. So, not far away, low value. Look at this one up here. Okay, how far away is it? Pretty far. How fast is it going? Pretty fast. So the trend we're seeing is the further you are away, the faster you're going. Write that down. Don't write it the other way. Okay, This is the independent variable, and the dependent variable depends on that, yes? So the speed depends upon the distance away, not the other way around. Stop mucking around. The distance doesn't depend on the speed. The speed depends on the distance. The farther the galaxies are away, the faster they are going. Okay? And that's what Hubble observed. Okay? So he came up with Hubble's law, which says exactly that, but it's a little more elaborate. The speed with which objects in the universe move apart from each other is proportional to their distance from each other. The universe is constantly expanding. And this caused a huge problem for steady state, because if everything's expanding, eventually everything is going to get far enough away from each other that you won't actually really be able to see anything. The distances will be just too great. But if you look out into the night sky using a telescope, it's full of matter. Sure, there's big gaps, but there's also a heap of things there. And so that was a problem for steady state theory. So they came out with a terrible alternative, steady state 2. They said everything moves apart, sure, that's observable, but every so often new galaxies just pop into existence. Pop. Bang, galaxy, 400 billion stars, all rotating around a supermassive black hole. Pop. And no one has ever observed a galaxy forming like that. There are no laws for how that might work, nothing. It is not a good idea at all, okay? But the other alternative theory that came through, and is the theory that we work with, is the Big Bang theory, which is the universe started with a small singularity, then inflated over about 13.8 billion years to what we see today. It had a start, it will have an end, and there's debates about how it's going to end. Is it going to slow down and then crunch back together? Or is it going to expand, and everything cools down, gets sucked into black holes, and everything dies an exotic heat death of no atomic motion? There's a video on YouTube of Santa Claus, and it starts off with pointing out that Santa is immortal, he is eternal. Okay, and you see Santa walking around a world where there are no humans anymore, no children to give toys to. And by the end of the movie, Santa's floating out in space, and there's this little light of reflection in his eye as the universe dies, as it crunches down, and then it's gone, and he's still out there, just floating around. It's kind of grim.
Yeah.
Can we watch that?
I have never found it again, but it's cool. It's really well done. Big Bang Theory, 13.8 billion years, and then, these two guys, they did find some really compelling evidence for the Big Bang. So, what I want you to understand is, you need to understand Hubble. Hubble's observation is strong evidence for an expanding universe, and it provides evidence that the Big Bang occurred. Okay, but his evidence is really the universe is expanding. But from there, physicists ran with that. Okay, if there was a Big Bang, we know what the universe looks like now, so what would the conditions have been like then? And they're crunching numbers and doing maths and coming up with different ideas, and a few decades passed, and they came up with, okay, the universe would have had to have been like this at the beginning, okay? And so one of the pieces of evidence for the Big Bang is the amount of really helium that you have in the universe. And the amount of helium that exists now is evidence for the Big Bang, okay? It couldn't have occurred in a natural way that we understand helium to be made in stars. So the first point of evidence for the Big Bang is difficult for students to understand. It's just the amount of helium that's in the universe at this time could only be if the Big Bang had occurred. So that's a bit tricky. Does anyone have any questions about that? It's hard to word, and for students, and even at this level. The second piece of evidence is the cosmic microwave background radiation, or CMB radiation. Okay, these two guys I've forgotten the experiment they were trying to conduct. Pretty simple, at a radio telescope. They were trying to set things up, and they were calibrating their equipment, and the equipment was what we would interpret to be like humming. Like they were picking up a signal, and they should have had no signal. They were looking at deep space, nothing visible. There should have been nothing at all. And they thought, oh, there's a problem with the equipment. Take everything apart, put everything back together, got a hump. Take everything apart, add one new component at a time, got a hump. Get up on the telescope, scrape off all the bird poo, okay? Climb back down, got a hump. Spend a year doing that. That's science, trying to eliminate the hump. And they got a Nobel Prize out of it, so it was worth the effort. The hum was effectively the echo from the creation of the universe. Every direction they were pointing, they were getting that hum, because that's cosmic microwave background radiation. Okay, when the universe formed, the leftover heat radiation ultimately saturated the universe with this microwave radiation. More accurately, actually that number's wrong. That should be 14 billion years, because it's at 13.8. The universe would have a temperature of 2.7 degrees above absolute zero. Wilson and Arno Penzias discovered CMB by accident. It's not the other two, it's these two. These particular individuals, Wilson and Penzias, discovered the cosmic microwave background radiation. But gamma and alpha, they were the ones who predicted its presence. So they crunched the numbers, they worked out that the universe should be a little bit warmer than you would expect, at 2.7 degrees above absolute zero. These particular astronomers confirmed that prediction. Okay, and that's the way science works. People will make a prediction that's testable, and then other people will go and look for that, or the same people will look for that. And if they find that evidence, then your theory gets stronger, okay, and gains greater support. So what this CMB showed is the universe definitely had a start. Matter wasn't evenly spread, but it ultimately clumped together to form galaxies. And those two key pieces of evidence were instrumental in providing evidence for the Big Bang. This particular picture here is a heat photograph of the entire universe. That is the entire universe. That is more than one picture stitched together to produce a heat map of the universe. The darker the blue, the colder it is. Okay? And all of these smatterings you see around here are galaxies. Okay? Or maybe many, many groups of galaxies and superclusters. This thing down here is interesting. It may be a bruise from when the universe bumped into another universe. So there is an idea out there, but it's not really testable, that there may be a multiverse consisting of many universes. For a long time, galaxies weren't discovered. People didn't know about galaxies. They just thought there's stars up there, we're on a planet, you know, whatever that might mean. And galaxies were ultimately discovered to exist. And a better idea of the universe came from that, obviously. And some people have hypothesised that there indicates that there is more than one universe out there as well. There is no meaningful way to test that. We can't get outside this universe. Obviously, we're on the skin of the balloon. We're an ant on the skin of the balloon. Okay. Many, many, many good sci-fi movies revolve around that concept of how could you get faster than light speed travel and things like that. Could you go through the balloon to get to the other side? You know, could you go through another dimension of space and then pop back into our space and things like that? So, and possibly that might be possible, I suppose. But not with our level of understanding of how things work at this point. Any questions at this stage? So I think was that the last slide? Yeah, that's the last slide there. We'll watch a couple of videos to help you cement all of this information that we've covered at this stage, and